So today we will discuss motion of particle in Cartesian coordinates. Okay. So for that, we mean here we will be dealing with motion of the particle in two dimensions. Earlier we have dealt with motion of particle in single dimension. Now we will deal with motion of particle in two dimensions, and particularly we will just study here Cartesian coordinates expressions. Okay. So suppose this is the plane where the motion of a particle will be studied. So suppose this is the path followed by the particle. So P at any instant t, P is the position of the particle. At other instant t plus del t, Q is the position of the particle. So suppose it is xy and this is x plus del x, y plus del y. Okay. And so I am saying from P it has traversed to the point Q in time del t. So what is the, you can easily understand that while we are talking about two dimensions, we are seeing the change of the particle P along two axes, we can say. What are the two axes? If it is moving from P to Q, then x is changing to x plus del x, and also y is changing from y plus del y, and these two are independent. These are axes, so these two are independent perpendicular lines. So we need to study both these changes. So one change is taking parallel to x axis, another taking parallel to y axis. Okay. So I can say x is changing to x plus del x, right? In del t time. Okay. So that means if the rate of change I consider along x, then this is the rate of change. Now, if I take limiting condition of this, that means when time is very small, instantaneous if I consider, then what I will get? I will get dx dt. Let me just write it here, equal to dx dt. Rather, we also use this symbol x dot. Similarly, I can say del y, del t rate of change of the position of the particle with respect to the y-axis. That means parallel to the y-axis. What is the change in the displacement of the particle with respect to time t? And then I take the limiting condition. That means when t is very small, change in t is very small, then we get y dot. So these are the velocities with respect to parallel to y-axis, velocity parallel to y-axis, and this is similarly parallel to x-axis. So we know the velocity is a vector, so we can write velocity v equals to vx along I plus vy along j. What is vx? Just we have seen right now, it is x dot, and similarly y dot. Okay. So this is the velocity of the particle. So you can easily find out the resultant or the angle in between the two components like that. Now similarly, let us now see the acceleration. So what is acceleration? Change of velocity. That means here also, if the velocity is changing in two directions, velocity, if the particle is moving from P to Q, okay, any change in the position, we are measuring with respect to two axes. So obviously acceleration will also be measured with respect to the two axes. So we will again get two components of acceleration. And now how to get these two components? This is very straightforward because we are saying the acceleration F is nothing but change or rather variation of velocity. So that means d dt of Vx, and let me just write the complete vector notations only. So plus d dt of Vy. Okay, that means what you are getting here. This is x dot. So x d2x dt2. Similarly, d2y dt2. And we often or rather most commonly we refer to or symbolize it as x double dot and y double dot. So this is, I may say, this is my fx and this is my fy. In limiting condition also you can think of it, because if v is changing with respect to x, that means vx is changing. Vx, from vx we go to vx plus del vx. Okay, so I am studying the change of vx with respect to t whilst I am calculating the acceleration of the particle with respect to x. That means if I am calculating fx, that means I am studying the change in this with respect to t. That means I am actually studying vx plus del Vx minus Vx with respect to t. So this thing. And then I'm applying the limiting condition, assuming the change in time is very small. So that means ultimately what do you get? Del t tends to 0, del Vx by del t, that is actually this x double dot. Okay, similarly for the y. So here we are getting the idea that if you want to study the motion, now we already know from beforehand, while we try to study the particles motion, what we need? We need to frame the equation of motion. Now to frame the equation of motion, what do you need? The accelerations, expressions. So we now know how to express the acceleration, also how to express the velocity. Okay, now we can easily use them in our formation of equations of motion in two-dimensional motion of the particle. Okay, so let us just go through quickly with this PDF. So here, as I said, they are just first deriving the expressions of this acceleration and velocity. Here we have considered the conventional perpendicular axis. But the thing is, it is not mandatory that you consider perpendicular axis. You can also consider oblique axis. Okay, you will get same expressions. And also you can just, if you have noted down carefully, while we are deriving all these things, we never use this axis to be perpendicular. We only use the limiting concept, okay, and the rate of change of some quantity with respect to other quantity. That other quantity is obviously time in our case, okay. So it need not be perpendicular axis. It is also valid for the any oblique axis, okay. So once we have got all these expressions, I have just shown all these things. So you are getting things like this d2y dt2 and then this d2x d2, okay. And alternatively, you can express like this also. That is d2x dt2 can be expressed as a product of the velocity term and the change of velocity with respect to x. Okay, actually, why we are just stating it right now at the very beginning, because it depends on the problem, which expression you use in the sum you are doing it. It depends on the requirement which you face. Okay, so we or interchangeably use this, sometimes this one, sometimes this one. Okay,